Welcome back to the deep dive. Today, we are stepping into a scenario that I think pretty much every developer, regardless of what language you code in, has had nightmares about.
Oh yeah, the classic Friday afternoon setup.
Exactly. You've written the code, it looks clean, it passes all the unit tests, you push it to a live environment, and maybe you're feeling responsible, so you run a quick load test.
Oh, boom. The screen just goes red.
Yeah.
And it's not the good kind of red where you just fix a typo and move on.
Right. We are looking at a really fascinating piece today from Aaron Rose titled The Secret Life of Go, the Mutex. And it introduces us to this character named Ethan. Ethan is currently staring at his terminal in just absolute defeat.
We've all been Ethan.
We really have. He has a server that crashes, hard crashes every single time he puts it under load.
And the worst part about this specific crash is the error message itself. It isn't a graceful, 404 not found or a connection timeout or something.
Yeah.
It is a runtime panic.
Yeah, the specific error message here is really the villain of our story today. It reads, fatal error, concurrent map read and map write.
Just hearing that makes me sweat a little bit, honestly.
It feels like the compiler is just screaming at you. So our mission in this deep dive is to unpack exactly what that error means, why it's happening to poor Ethan, and how we solve it using a tool that is absolutely essential for any Go developer.
The Mutex.
The Mutex.
Right. And I think this is a really important pivot point for people learning Go. A lot of developers come in, they learn about channels and coroutines early on, and they think, okay, that's it. That's how I do concurrency.
Like they've solved the puzzle.
Exactly. But today we are talking about shared memory. We're going to look at how to protect your data when you have, say, 1,000 things trying to touch it all at once.
So let's set the scene effectively here. Ethan has built a simple in-memory cache. Nothing too fancy, right?
Right. He's using a standard Go map.
Yeah.
Just a basic map string to store user data.
And he has a function called getUser. The logic is simple enough. You check the map. If the data is there, you return it. If not, you fetch it from the database, save it to the map, and then return it.
It's a very standard pattern. We call that look-aside caching. It's the bread and butter of back-end development, really, because calling the database every single time is just way too slow.
Right. And it works completely fine when he runs it locally, maybe curling the endpoint once or twice. But then
Decides to stress test it.
yeah, he fires up dozens of coroutines calling getUser all at the exact same time. And that's when the server just completely melts down.
This is where we need to peel back the abstraction layer a bit. We need to understand exactly what is happening under the hood here.
Because it's not obvious at first glance.
No, it's not. The core issue, and this is a deliberate design decision in the language, is that Go's standard map implementation is not thread safe.
Okay, let's unpack not thread safe, because you hear that term thrown around a lot. What does that actually look like in the memory? Is it just overwriting data?
It's actually so much worse than just overwriting. Imagine the map isn't just a simple list. It's a complex structure of buckets, hash tables, pointers.
Lots of moving parts.
Exactly. So when one coroutine is trying to write a new entry, like cache-id equals data, it's literally moving bytes around. It's allocating memory, maybe even resizing the entire hash table if it's getting full. It is performing surgery on the data structure.
Okay, so it's in the middle of open heart surgery on the memory.
That's it. And at that exact microsecond, another coroutine tries to read from that same spot. It tries to walk a pointer that is currently being moved or even deleted.
Wow. So it's like trying to cross a bridge while the engineers are physically moving the planks to a different location.
That is a perfect analogy. You just fall into the void. The memory gets corrupted because the read happens while the write is only half done.
The data is in an invalid state.
Right. Now, in languages like C or C++ key, you might just get garbage data back, just pointer soup, and you wouldn't know why your program is acting weird for weeks. It would be a totally silent failure.
Which sounds terrifyingly difficult to debug.
It is literally the stuff of nightmares.
Yeah.
But Go is designed to be safer. The runtime actually has a built-in detector for this. It detects this race condition, this simultaneous read and write, and it intentionally panics.
It pulls the emergency brake?
Yes. It crashes the program immediately to prevent you from continuing with corrupted memory. It feels like a disaster to Ethan, but it's actually a huge favor. It's telling you, stop. You are doing something dangerous.
So Ethan is looking at this crash, and he's confused. He turns to his mentor figure in the story, Eleanor, and his first reaction is one I think a lot of us have had. He says, wait, I thought Go is built for concurrency. Why doesn't the map just handle this out of the box?
That's a very common reaction. Why isn't it safe by default? And the answer is usually performance.
Right, because safety has a cost.
Exactly. Making every map operation thread safe adds overhead that you don't always need. If you're using a map inside a single synchronous function, you really don't want to pay the compute cost of locking.
But Ethan brings up another point, something we've actually talked about in previous deep dives. Channels.
Right. He asks Eleanor, should I just put this map behind a channel? You know, the famous Go proverb, share memory by communicating.
It's a very catchy slogan.
It is. But Eleanor gives him a really crucial mental model here to distinguish when to use what. She says you have to look at the nature of the data interaction. Channels are like a conveyor belt. They are for moving data from point A to point B.
Like passing a message, handing off a task. Here, you take this.
Exactly. But in this case, Ethan isn't trying to move data. He has a bucket of state, the cache, that needs to sit in one place and be accessed by everyone randomly.
And when you need to protect state that stays put, you don't use a conveyor belt, you use a lock.
Precisely. Eleanor explains that while channels control the flow of data, a lock controls time. It controls when a task is allowed to touch a specific piece of memory.
That is a great heuristic. If I'm sending data to another process, I use a channel. If I'm protecting a shared resource that sits still, I use a mutex.
That's the golden rule.
So let's introduce the hero of the day, sync.mutex. Eleanor imports the sync package. Now, I love the analogy you used when we were prepping for this deep dive. You called it the digital bouncer.
That is essentially what it is. Mutex stands for mutual exclusion. It literally means I am excluding everyone else.
Imagine a velvet rope in front of that map. Only one Go routine is allowed past the rope at a time.
So, practically speaking, how do we use this bouncer? Is it a complex setup?
It's surprisingly simple. In Go, the sync, mutex is just a struct. And here's a cool implementation detail. The zero value is useful immediately.
Oh, meaning you don't need to make it or run an init function.
Right. You just declare var musync mutex and it's ready to work.
That's convenient. So you just declare it right next to your map.
Usually it sits right above the map, inside the struct definition. Then inside your getUser function, right before you touch the map, you call mu.lock. That's you asking the bouncer for permission to enter the club.
And if someone else is already inside,
Your Go routine blocks.
like it just stops. Yes. And blocks is a technical term here. The Go scheduler literally pauses your Go routine. It stops running on the CPU entirely. It sits in a waiting line until the lock is free.
So it's not spinning and burning CPU cycles, checking the door handle over and over again.
Generally, no, it's put to sleep. It is highly efficient waiting.
And once you're done doing your business in the map?
You call mu.unlock.
Yeah.
That's you leaving the club and letting the bouncer know the next person in line can come in.
Okay, but there's a massive trap here, isn't there? A safety rule that Eleanor emphasizes, and honestly, I see people mess this up in code reviews all the time.
The lost unlock. It is the single most critical rule of using mutexes. You have to ensure that unlock always happens.
Because if it doesn't?
Imagine if your code enters the VIP section, locks the door, and then the function panics. Or maybe you just hit an early return statement because of some basic validation error.
You left via the back door, but you still have the key in your pocket.
Exactly. The lock remains engaged. The bouncer thinks you're still inside. Every other Go routine that comes along and calls lock will wait forever. They will just pile up at the door.
That is a deadlock. The application just freezes. No CPU usage, just complete silence.
It stops completely. That's why Eleanor introduces the defer keyword here. It is non-negotiable. Immediately after you write melock, your very next line should be defer mu, unlock.
And defer basically means run this cleanup code right before the function exits, no matter how it exits.
Correct. Even if the function panics, defer still triggers. It guarantees the lock is released. It's a safety net you should really never code without.
So Ethan implements this. He adds mu-lock at the start, defer mu-unlock immediately after. He runs the load test again.
It's success. No panic. The server stays up, green lights across the board.
Victory! But come on, it's a deep dive. There's always a but.
There's always a but. Ethan notices something new. The server isn't crashing, but it's sluggish. The response times have gone up significantly.
He fixed the corruption, right?
He did. But he created a bottleneck in the process. Think about the bouncer analogy again. A standard mutex is a strict one-person-at-a-time policy. Even if 100 coroutines just want to read the cache, just check if a user is there. They have to wait in a single file line.
But reading is safe. You said earlier that corruption happens when you read and write at the same time. If we're all just reading, we aren't changing the structure. We should all be able to look at the list together.
Exactly. Reading doesn't corrupt memory. So forcing readers to wait for each other is incredibly inefficient. It's a blunt instrument, as Eleanor calls it. You're applying maximum security to a public library reading room.
So we need a smarter bouncer, one that actually knows the difference between a reader and a writer.
Enter the sync.rw mutex, the read-write mutex.
This sounds like the upgrade Ethan needs. How does this one differ from the standard mutex?
The RW mutex has two different types of locks built in. There's the standard lock for writing, which is exclusive, nobody else allowed. But there's also R-lock, the read lock.
And R-lock is the party mode. Sort of, yeah. An R-lock allows infinite simultaneous readers. If 100 Go routines want to R-lock, the bouncer waves them all in at once. Come on in, look at the data, have a good time.
Okay, that definitely solves the bottleneck. But what happens when someone needs to write? Because eventually we have to update the cache.
That's where the coordination happens. When a Go routine calls the main lock, the write lock, the bouncer, changes the rules. First, it stops letting any new readers in. It puts up the velvet rope for new arrivals.
Okay.
Then it waits for all the current readers to finish what they are doing and leave.
So it clears the room.
It clears the room completely. Once the last reader unlocks, the writer gets exclusive access. Nobody else, reader or writer, can enter until that writer is done.
That is incredibly clever. It prioritizes safety for writes but maximizes throughput for reads. So Ethan switches his code to use sync.rw mutex. He uses rlock to check the cache and lock when he needs to update it. Right. But, and this is where we get into the really deep part of this deep dive, Ethan runs into a logic trap. A very dangerous nuance that catches a lot of developers, even senior ones.
I love a good logic trap. It's like a puzzle. What does he try to do?
Well, look at the flow. He uses rlock to check the cache. Is the user here? The answer is no. Okay, now he needs to fetch the data and write it to the cache. So he thinks, I'm already holding a read lock. I'm already inside the room. I'll just call lock to upgrade my pass to a write lock.
That sounds completely logical. I'm already inside. Just give me the manager badge so I can edit the file.
It sounds logical, but it is deadly. Eleanor warns him right away, go forbids atomic lock upgrades.
Why? That seems like such a useful feature to have.
It's to save you from yourself. Imagine two Go routines, both holding a read lock. They both see the data is missing. They both decide, hey, I need to write this. They both try to upgrade to a write lock at the exact same time.
Oh, I see where this is going.
To get a write lock, you need the room to be empty. Goritin B is waiting for Goritin B to leave so it can write. But Goritin B is waiting for Goritin A to leave so it can write.
They are blocking each other. Another deadlock.
Exactly. A classic embrace of death. So Goritin forces you to do it the hard way. You must release your read lock completely, call run lock, step out of the room, and then request a write lock by calling lock.
Okay, so the sequence is check with read lock, not found, release read lock, acquire write lock.
Correct. But there is a massive hole in that logic.
There is. It sounds safe. You unlock, then you locked.
Think about the gap. The millisecond between releasing the read lock and acquiring the write lock.
Oh, in that split second, you're not holding any lock.
Exactly. The bouncer has let you out but hasn't let you back in as a writer yet. In that tiny window, another Go routine might have slipped in.
So while I was standing in the hallway, someone else could have grabbed the write lock, fetched the data from the database, and populated the cache.
Bingo. And if you don't check for that, you enter, you overwrite their work, or you perform a redundant, expensive database call that you didn't even need to do.
That is subtle. So basically, you check the cache, see it's empty, leave the room to get your writing tools, come back. But by the time you come back, someone else might have already filled the cache.
That's it. And this leads to what Eleanor calls the double check pattern.
The double check. So once you get that write lock, you have to look at the map again.
Yes. It looks a little weird in the code, but it's absolutely necessary. You call lock. And the very first thing you do inside that write lock is if val exists, cache-id, return val. You have to verify that the state hasn't changed while you were waiting in the hallway.
That makes total sense, but I can see how easily someone would forget that. You feel like you already checked. You think, I just checked it a microsecond ago.
It is likely the most common bug with RW mutexes. You assume the world hasn't changed, but in concurrency, the world changes fast. If you miss this, you get what we call the thundering herd problem.
The thundering herd.
Yeah, where 50 Go routines all realize the data is missing at the same time, and they all hit the database one after another, even though the first one actually fixed the problem.
Which defeats the whole purpose of having a cache in the first place.
Exactly.
So Ethan implements the double check. He's got his RW mutex. He's got his defer statements. He's properly upgrading his locks by releasing and reacquiring. Is he done? Is this the perfect solution?
It is the correct solution for his specific problem, but we should definitely talk about trade-offs. Ethan notices that while the RW mutex is faster for his read-heavy workload, Eleanor drops a little reality check on him.
Which is what?
An RW mutex isn't free. In fact, it's much more expensive than a standard mutex in terms of complexity and CPU overhead.
Because it has to track all those readers.
Exactly. It has to do a lot more counting. How many readers are inside? Is a writer waiting? Who came first? That takes CPU cycles. It also introduces something called cache contention at the processor level if you aren't careful, balancing the lock status between CPU cores.
So it's a heavier tool. You don't just use it blindly for everything.
Yes. Eleanor's rule of thumb is use RW mutex only if your reads massively outnumber your writes. We're talking 90% reads, 10% writes, or even more skewed than that.
What if I'm writing a lot? Say, a 50-50 split.
If you write frequently, the standard sync mutex is actually faster. The overhead of the RW mutex isn't worth it if you're constantly clearing the room for writers anyway. You're just paying for complexity you aren't using.
That is a great takeaway. Don't just default to the fancy tool because it sounds more concurrent.
Right. Simplicity often wins. If a simple lock works and is fast enough, use the simple lock. Don't add the complexity of the double check pattern if you don't need the massive read throughput.
So, to synthesize the journey we've been on, we started with a crashing server due to concurrent map writes. We learned that sync mutex is the bucket protector, the digital bouncer. We learned that defer is non-negotiable for avoiding deadlocks. And we learned that sync.rw mutex is great for read-heavy loads, provided you remember the double check pattern and don't fall into the upgrade trap.
That's a very solid summary. And honestly, if you can master those concepts, especially the double check, you are way ahead of a lot of Go developers out there. It's one of those things that really separates junior developers from senior engineers.
It feels like Ethan, and hopefully you listening now, has a much more complete concurrency toolkit.
Definitely. You have channels for passing data and mutexes for protecting state. Understanding the difference, knowing why you are using a tool, is what separates a coder who just pastes solutions from an engineer who actually designs systems.
Well said. Now, before we go, the source material leaves us with a bit of a teaser, a provocative thought for you to chew on.
It does. We spent all this time talking about how to wrap a map in a mutex to make it safe. But there is a situation where even the RW mutex might be too manual or too slow due to that cache contention we mentioned earlier.
And the teaser is sync map.
Yes. Go actually has a built-in concurrent map called sync.map. It's not for every situation. It's actually specialized for cases like append-only caches or when keys are mostly disjoint, but it allows you to skip the mutex entirely.
Interesting. So maybe next time you're reaching for that mutex, take a second to look up sync.map and see if it fits your specific problem. But for now, master the mutex. It's the foundation of safe Go programming.
Absolutely. If you understand the mutex, you understand the machine.
Thanks for diving in with us. We'll see you on the next one.